Hello, my name is Anvar, and in this video I will give you an example of what you are going to do during our class. Today we will analyze the Titanic dataset, which contains information about passengers from the Titanic ship, and I will walk you through three important steps of creating a working prediction model, exploring the data, fitting an algorithm, and assessing its quality. So let's start. So first, let me show you a couple of cool Jupyter Notebook features. So if you are familiar with a command line, you could actually use a command line, and you could actually type command line commands inside the Jupyter Notebook by prepending them with an exclamation mark. So for example, there is an ls, and also there is a pwd command, and you could also install some Python packages if you're missing something by typing pip install and then package name. And the second cool thing is that Jupyter Notebook actually has two different keyboard input modes, and by default you're in the edit mode, and in the edit mode you're just typing some letters or writing some code, but there is also a so-called command mode, and you could enter command mode by pressing an escape button, and in this mode you could use Jupyter Notebook shortcuts. So for example, escape and B will create a new cell below current cell, and escape A will create a new cell above current cell, and you could also use your arrows to move around. So it's pretty cool. You could also delete cell by pressing escape X, and so on and so forth. So for a complete number of all shortcuts, you could press escape and H, and you could learn them from here. Okay, let's move on. So as I tell you, we will analyze the Titanic data, and we will start with loading the data. Load the data, and we will use a pandas package to load the data. Pandas is actually a very popular Python library to work with tabular data. So basically this is a Python version of Excel, but much more powerful. And we could read the data using read CSV function, which takes as an argument a complete path to the file. So for example, pd read CSV, so the file name is Titanic data, and let's put it into some variable. You could either use a complete path, or we could use a relative path if the file within the same folder as the Jupyter Notebook file, right? So for example, we could use a complete path to the file. It makes no difference at all. Same exact file. So let's see. Let's explore the content of this table using a head command. Def head. So this method shows you first several rows of the table, and you could provide an integer number as a parameter to specify number of rows. So for example, if I put 3 here, it will show me only the first 3 rows of the table. We could also assess the columns of this table, df.columns, so all the column names, and we could, like, as you can see, by default Jupyter Notebook prints out value of the last line within the cell. So you could either assign this value to some variable, for example, columns equal to df.columns, and then print this, and then print this value, columns print, right? Or you could type a semicolon in the end to avoid printing, right? Columns, semicolon, no output at all. Okay, so let's move on. We could check the size of this table by using a shape. So in this table there are 1,309 rows and 12 columns. And finally there is a pretty useful method called count. It shows you number of non-missing values in every single column. So for example, if I show you last rows of the table using a tail command, let's say last 10 rows of this table, we could see that some of the rows actually have no values within the column age, right? Which means that there is no information, there is no data about an age for some of the passengers. And dealing with missing values is a pretty important processing step, and it will highly affect the resulting machine learning predictive model. Okay, let's move on. So if we want to access some specific column, we could do that either by using a dot operator, simply put df dot and then the name of the column, for example, column sex, or we could use square brackets. Again, there is no difference at all between these two methods, except if your column have a space in its name, for example, it's a passenger class, right? Then you couldn't use the first way, right? Only like here. Also, we could access individual rows by using an iloc. So this is a single row, a very first passenger. The first row has index 0, as always in Python. So this is a row corresponded to the very first passenger. Yeah. Okay. Also, we could access slices of rows. Again, pretty similar to the Python lists. Let's say like this. Pretty cool. Okay, let's move on. So next thing, what we're gonna do, we will actually build a baseline model. So instead of doing an exploratory data analysis and like looking for some patterns in the data and only after this building a model, we will start with building a baseline model. And let's call it build a baseline model. And this is actually so-called markdown cells. This markdown cells allows you to type text in and use HTML commands, and use some LaTeX commands also. Pretty cool. So the whole purpose of machine learning is to predict some target variable y, and in this case it's column survived, whether the person of the shape survived the sync or not, based on some set of features, in this case like passenger class, name, sex, age, and some others. For the baseline model, let's only use the numerical features, right? So if we speak about some kind of machine learning, it's there is some math behind them, and probably this math will not work with strings, with names, right? Or that would be weird. So let's for our baseline model, let's only use the numerical features. So how do we know which features are numerical? We could access column types from the attribute dtype. Dtype will show us, so let me add some more cells. So we could see that there is actually only 4 numerical columns. It's age, number of siblings and parents, and passenger fare. The passenger fare is basically a price of a ticket. Okay, so let's create a separate variable containing all the names of all numerical columns. Age, number of siblings and spouses on board, number of parents on board, and passenger fare, right? Yeah, and what we want to predict, we want to predict based on these columns. We want to predict column survived, right? Okay. So what we're gonna do next, we need to select some machine learning model, and we will use a decision tree classifier. This is a pretty simple rule-based algorithm. You will have a whole lecture about decision trees and how to build them, but for now we will just use them as a black box model. Yeah. So for this model we will use a scikit-learn package, scikit-learn library, which implements all core machine learning algorithms in some kind of a uniform form. And so the decision tree algorithm imported from the sklearn tree, and decision tree classifier, and we will also need a train test split function from the sklearn model selection. So train test split is literally splits our data, our table into 2 tables. One we call a train set, and another we call a test set. And we will train our model on the train table, on the train data, and we will assess the quality of our model on the test set. And again, you will have a full lecture on this like train test splitting thing, but just for you to understand the idea, imagine you have a math class and you have a home assignments and an exam, right? So the tasks during the exam should not be exactly the same as the task in the home assignment. They should be similar but not the same. Why? So because your teacher doesn't want you to memorize the answers, right? They want you to learn some mathematical laws, some mathematical rules. So same idea goes here. We don't want our model to memorize the data. Instead, we want it to learn general patterns. That's why we train our model on one data, and then we assess its quality on the unseen data. Okay, so train y test equal train test split. What should we put here? Num columns, right? And df survive. And let's say we want our training part to be about let's say 2/3 of the data, and let's fix a random state for reproducibility purposes. So this number here is rather arbitrary. It could be 3/4, it could be 90% of the data. This number means that approximately 66% of the data will go into the training part, and 34% of the data will go to the test part. Okay, let's run this cell. So let's see xtrain. This is the table. What is shape of this table? Okay, it's 863, and originally we had 1309, so it's about right. Yes. Yeah, it's about 66%. Okay. So same for the test part. So this is a test table, this is a train table, and we also have two columns, y train of the same size as the train, and y test of the same size as x test, right? Okay, cool. So now we need to create a classifier, and we will create a decision tree classifier with parameter max depth equal to 5. Again, so you will have a full lecture about decision tree and all the details about the parameters of this machine learning model in the future lectures. So for now, let's just select some parameters, and we save it into some variable called CLF from classifier. Once we do that, we could train it. We could so the training part is the method fit is responsible for the training the model, and it takes two parameters, x's, so the data, and y's, the target variable. So you show your algorithm some features and the corresponding answers for these features in order to train this algorithm, and then we will predict this target variable on an unseen data. Oh, okay, something goes wrong. So the problem is our input data contains some missing values. So if you remember, we had some missing values within our data. Let's check. Count. So basically column H is missing some values, and column passenger fare missing a single value. Okay, let's fill them up. So let's start with an H column, and there's actually many ways to deal with missing values, and probably the worst way to deal with them is to just drop them. It's a possible way, but typically it's not a good idea. So what we do here, we will fill them up with average value from the same exact column. Okay, so let's say again, so for example we have this missing value, and we fill all the missing values within the column age, right? In this column we fill them up with a same value, and this value is an average age across the whole trained data set. Okay, so let's compute a mean age. Mean age equal to x train age dot min, right? And now what we're gonna do, we will say that x train age is equal to x train age fill NA, so fill missing values with mean age, value equal to mean age. And by the way, if you put your cursor inside the brackets and press Shift Tab, you will see a signature of the function, and if you press this arrow, so this window will pop up, and you will see all the parameters of this function fill NA, along with the docstring and the description of these parameters, and also some examples of some usage examples. Okay, it's pretty useful. So again, put your cursor inside the brackets and press Shift Tab. Okay, so this is for age, and also we should do the same thing for passenger fare. So mean fare equal x train passenger fare dot min, and again passenger fare equals to passenger fare, but with filled missing values. We run this cell, and now we could fit our classifier. We could train our classifier. Okay, again, okay, my bad. It should be x train, not x test here. All right. Okay, now we are good. So we train the classifier, and now we could predict the target variable of an unseen data. So let's do that. clf.predict. So again, we have train data, we have test data. We train our classifier on a train set, and we assess the quality of our classifier on the unseen data x test. So recall that clf.fit takes two parameters, x train and y train, and clf predict takes on this one parameter, it's x test. It's a features for which we want to predict the target variable. So let's predict. And again, we have exactly the same error. Exactly the same error because we need to fill the missing values also in the test part of the data. So let's do that. And so we actually need to use average values from the training part of the data. This is the proper way to do that if we want to fill missing values with averages. And this relates to the problem called overfitting, or some it's a memorization. And again, we will tackle this in a later lectures. So just for now, we just do it like this. So x test age equals x test h dot fill and name, but we take value from the training part. So we already have this variable mean age. By the way, let's see. Okay, so the mean age of the passengers was about 30 years. Mean age. Same goes for passenger fare. Let's copy it from here. Let's change it to test. Nice. And here should be fare. So that was a typo. Let's rerun this cell. Let's remove this cell. Let's fit our classifier one more time since I have a typo here. Value mean fare. Sorry. Now we could predict. Cool. So we successfully predict values for the subtable X test. Let's save it to some variable y predicted, y pred. So now we need to assess the quality of our predictions, right? And how could we do this? So, for example, what we could do, we could simply compare every single prediction with the actual y value, right? We have y pred and we have y test, and we could compare them one by one. So let's do that. For true predicted and zip y test. So first value will be the real one, the right one, and the second one will be the predicted one. Print true predicted. Okay. So as we can see, sometimes our predictions are good. So for example, here the person did not survive and our model said that he's not survived, and here it's vice versa. The person survived and our model predict that he will survive. But sometimes it's not, right? So for example, here the person survived but model said no, and I'm sure there should be some like vice versa cases when person actually died but our model said that he or she did survive the crash. So what we want to do, we want to compute some number that will hopefully tell us how good or bad is our model. And as for this number, we will use an accuracy metric, which is simply a number of times when our prediction is right, when our prediction is exact, divided by total number of predictions. So it's simply a ratio of right answers. We could import it again from the sklearn. Let me add more cells. So from sklearn metrics, import accuracy score, and then we could compute it. Y test, y pred. So what this number means? So accuracy scores differs from 0 to 1, with value 1 means that the predictions is perfect, right? So for example, accuracy between y test and y test is 1, right? If your classification task is balanced, so the number of zeros and the number of ones is equal, then the random guess model will give you a 50% or 0.55 accuracy, right? So this number here, 0.67, looks not too bad. Like, at least it's better than a 50-50, right? But remember that this is a Titanic, so most of the passengers actually died during that day. So let's check this out. Like, ytest.valueCounts. So you see this is a test subset, and if we take the whole data table, survived.valueCounts, it tells us that in this particular subset of the data, and this is not the whole, this is not only, like, this table contains only a subset of passengers from the Titanic, and the picture is even worse if we look for all of the passengers. So most of the passengers actually died there. So what if we instead this whole procedure with training a decision tree model, what if instead we simply always predict survived equal to no, right? So what will be the accuracy there? So let's do this. Let's create a variable no. It should be no how many times. So ytest.shape is equal to this thing. And now we could compute an accuracy score. Ytest versus ypred const. Right? So it's 0.62. So our number 0.67 is actually like it's already an improvement of a random guessing, but maybe we could do better. And in order to do better, what we will do, we will generate new features, or maybe we use some kind of processing for the already existing one. Anyway, we need to analyze our data. We need to use a technique called exploratory data analysis, maybe compute some additional statistics, or build some graphs to understand data better. Let's type it: exploratory data analysis, or EDA. So for this part of the lesson, we will use a sklearn package. Sklearn along with pandas package. So sklearn is actually a package to plot graphs, and it allows you to plot pretty good figures relatively easy. And you will probably have a separate notebook on visualization, but like for this part we just use some very basic plots. So we will start with a bar chart of survivors, right? So let's see some basic chart survived, and the data should be taken from the data frame df. So this count plot, and remember I told you about the semicolon in the end of the line. So if you put a semicolon here, it will remove this ugly message, because this function, this command here, is actually returns some object, and this plot here is a different thing. Okay, so command count plot creates a bar chart, and in this case it's a bar chart of a survived column, right? This column right here. So we could see that the every bar corresponds to a unique value in the column, and the height of the bar is the number of occurrences of this value, right? So again, we could easily check this survived dot value counts. It's about right? Okay, so this is our target variable, but what about other variables? Let's check the sex column, right? So let's plot exactly the same plot, but for the sex. So we only need to change the name of the column here. Let me add some more. So these two plots here, bar chart of the survived and bar chart of the sex, by themselves they're kind of useless, because the fact that the random passenger is twice as likely male than it's female doesn't tell us anything about the probability of them to survive, right? But what we could do, we could combine these plots, and we could plot a so-called cut plot, which is actually simply a bar chart, but within the categories. Survived sex kind equal to count, and data equal to the F. And what we will get, and let's put semicolon here, what we will get here is so actually those who had a probability class, they probably get the idea of what happens here. So we go from the probability of a survival of a random passenger. Let me show you these two pictures here. So we need to compare this picture and this picture. So on this picture, what we see is that a randomly selected passenger will most likely die, right? And this is P survived equal to yes, right? P survived equal to yes, right? But on this picture, so on this picture, we go from the probability over survival to a conditional probability of the survival given the fact that the passenger is a female or a male, right? And this is insanely useful information here, because there is no balance here. Once we know that the passenger is a female, we know that her chances to survive are about 2 times bigger than if it was a male, right? And so what this means? This means that if your algorithm, so we go from P survived equal to yes to P survived equal to yes, given that the sex is equal to, let's say, a female. So if your features, your axis includes sex, That means that your classifier, once your classifier see a person, a passenger who is a female, this classifier could learn that the female passengers are more likely to survive than the male passengers, right? Pretty cool. So that's for the sex. Let's do another categorical column. Let's say what column do we have? Let's say passenger class. Passenger class. So let's plot same plots here. And let's plot same bar chart here. So we have three different classes: first, second, and third. Passengers from the, so the first class is the most pricey class, right? So let's check that. df, we could do this the following way: group by passenger class, and let's compute passenger fare dot min, right? So what we do here, we compute an average price of a ticket for the passengers within a same class. So for the first class, the average price was $87. For the second, it was $21, and for the third, it was $13. Okay, so let's plot the same picture but for the passenger class and check if there is some kind of bias into one or another class. So again, it looks like, oh, my bad. So this should be survived and this should be passenger class, my bad. Yeah, it looks like again we could see that the original balance moved towards the passengers of the first class. So in a case, if you are a passenger of the first class, then your chances of survival are actually higher than your chances to die, and second, then like the chances of survival if you are from the second class or from the third class. Okay, let's move on. Let's visualize some. So we already visualized some categorical features. Let's visualize some numerical features. Let's say age, whether or not age help us to classify between those who survived and or not. So what could we do with numerical features? Unfortunately we can't plot a bar charts like that. But what we could do, we could plot a complete distribution of the values from some particular feature, for example age. So how we do that? We will use a seaborn facet grid. Facet grid. Again, put df here. We will have a survived here. So this thing will create as a figure, and then we could map any particular kind of a plot to this figure. This could look like slightly complicated, but it's actually not. Okay, let's improve the sizes of this picture. 3. Let's set some shade. Okay, much better now. So, which is what? Again, figure and legend. So which is what? So what this picture shows us is most of the times, it looks like most of the times age doesn't give us too much information except maybe for children, right? So let me explain it. So orange curve, this orange curve corresponds to passengers who died, right? So for every age value on an x-axis, let's say 20s, right? So all the passengers around 20 years old. We have a number, orange curve shows us a number of passengers of this particular age who died, right? And so this is a proportion, but you could think of this as a number. It's simply a number of passengers who died for the orange curve of this particular age. And the same is for the blue curve, but with numbers of survived passengers of this particular age. And so these two curves, they are almost always coincide, and there are some disparity at the at the 30s, and there is a huge difference here for the children's. So children's mostly survived, much more difference within this age range than, let's say, after 35 or something like that, right? So probably age is not completely useless, but not, I don't know, maybe not very useful. And we could partially support this this idea, this conclusion, by comparing the average age of the passengers who survived and who did not survive. So let's do that. Group by survived, age, mean, right? So basically these ages of the, if we split all the passengers into two groups, one group is all the passengers who survived and another group is all the passengers who died, and then we compute age within this group, average age within these groups, then we see that the average age is actually like pretty much the same. So let's go move on. So what's next? Age, sex. Let's take a fare, passenger fare. Maybe this feature will be much more useful than the age. Let's actually build the same plot for the fare. What can we see? Okay, so basically for the fare, we could see that like these distributions, they are far from being similar. They're pretty different, right? So another kind of simpler way to visualize this difference is to use a so-called box plot. Again, cborn.catplot x equals survived, y equal passengers fare, data equal to df, and kind, where the magic happens, is box. So this is a box plot, and what you could see is that, like, again, price of the tickets among those who survived is bigger on average than amongst those who do not survive. And as we speak about the prices, let's see. So there is something weird with these prices, right? You can see it here, and there is actually prices of 0, right? There are actually some passengers who do not pay at all. And who do you think are these passengers? So, for example, if we Google the very first person, it turns out that, okay, let me do that. It turns out that Thomas Andrews was a British businessman and a shipbuilder. So basically, this is the guy who engineered the Titanic. Okay, and he died. Yeah, not very lucky. And finally, again, we could show that. So being the passenger of the first class does not guarantee that you will survive. And finally, we could show numerically that the mean value of a passenger fare within the groups are pretty different, right? Group by, again, let me add some cells. Again, by survived, passenger fare dot mean. We could see that, like, the difference amongst the passengers who survived, the average price was like more than twice bigger. So you should actually be pretty careful with the averages like this, right? With computing averages like this, because this average value, it boils down the difference between two distributions. So we have these two distributions, and this average value, it reduces this difference between them to a single number. So if it is possible, you should always watch on distributions first, and then if you realize that there is a difference, you could compute some number. It could be a mean value, it could be a standard deviation, it could be some quantile or a median, many other statistics. But you should pretty much always start with a plot of a distribution. So what else do we have? A lifeboat. Yeah, okay. So the lifeboat, the column lifeboat, this attribute. First, this attribute contains most of the missing values. All right, if I remember right. Yeah. So the cabin and the lifeboat, and it actually contains. So actually, if the passenger ended up on a lifeboat, this attribute will not be empty, and otherwise it will be empty. So let's see, drop an subset equal to lifeboat. dot survived. Yeah, it's kind of obvious that if you ended up on a live board, you most likely survive, right? So I make some typo here. Drop an a subset. Yeah, it should be a list. So drop an a allows you to drop all the rows or all the columns containing some missing values. So what I want to do, I want to compute how many passengers who ended up on a live board did survive. Okay, so most of them survived. Some of them died, but most of them survived. And vice versa, amongst those who was not on the live board, number of survivors is negligible, right? So let's check this. Again, is an a returns us true if this particular row contains an a value. Let me show you. You see, so if the value is not a number or a missing value, which pretty much is the same, then is an a returns us true, and otherwise it returns us false. So again, we're interested in a column survived, and what we want to do, we want to compute the value counts. So we want to know how many of the passengers who did not end up on a live board actually survived. And you could see that only 23 out of 823 actually survived, right? So it's like a 2%, 3% of the people. And yeah, so most likely if you are not on a live board, you are dead. So what we will do, this attribute might seem pretty useful, but for today's analysis we will completely drop it, since typically in real life you do not have such a rich feature, but if you do, your job is basically done, but typically you don't. So typically y, the target variable, is there is no easy way to obtain it, right? And the x, so the features are like easily or not that easily but collectible, and we do have an access to them. And in this particular case, if you know that the person is on a live board, you could be pretty much sure that he or she will survive. So we will completely drop this feature, and we will also drop some other features. Let's see. So we will drop name, because I have no idea how to pre-process this column. We will also drop ticket number and the cabin. And so the ticket number and the cabin might be useful, but the problem with the cabin is that cabin contains too much missing values, and as you could see, it's a label, so it's a B5, C22, and sometimes it's a double cabin, so it's pretty hard to analyze it. It's for sure it goes beyond this video, so we'll also drop them. And for the remaining categorical columns, let's see what we do have. Let's create a list of them. So it's a passenger class, it's a sex, and it's a port of embarkation. So we do not analyze the port of embarkation too much, but let's leave it. Port of embarkation. So these are categorical columns, and we need to make to pre-process them to make them numerical, right? We need to somehow convert them to numerical. So there are many ways to do that, but today we will use so-called dummy encoding. So the idea of a dummy encoding is for a categorical feature with n unique values, we encode this feature with n binary features. So we increase number of features, but every single feature become a 0-1 feature, right? So let's see how we do that. Dummy columns equals pandas get dummies df cut columns, right? So this is our dummy columns. Let's compare them with the original categorical features. Df cut columns. So first of all, we had 3 features, and now we have 1, 2, 3, 5, 8 columns, right? We had 3 unique values of a passenger class, 2 unique values of a sex, and 3 unique values for the port of embarkation. So the total of 8 dummy columns. Let's see, for example, this very first passenger, it's a passenger from the first class. So passenger class first is 1, and these 2 are zeros. It's a female, so sex female is 1, sex male is 0. And the port of embarkation is Southampton. So the Cherbourg is 0, Queenstown is 0, and Southampton is 1. So it seems right. And we also have our numerical columns. Right, so our num columns, yeah, they are completely the same. So now what we want to do, we want to combine this dummy columns table with our numerical columns. What we will do that using a pandas concat function. Df num columns and dummy columns, and we want to concat them over the axis 1 and save the result to the variable called data. So let's see. This is our data table. It consists of 4 numerical columns, and then we have our 8 dummy variable columns. And the sizes of this data is, yeah, so all the rows of the original data, right? But the columns are completely different. So the number of columns is the same, but the columns themselves are different. Okay, cool. So we on the final lap. We want to build a new model using our new constructed table. Let's do that. Build a new model. So again, we need to split our data into xtrain, xtest, ytrain, ytest. Data df survived. Let me use the same parameters. Train size equal to 0.66 and state 5. So let me copy paste the code from this part. Okay, I'm missing something. Yeah, from here. So min age, x train, age, fuel and A, passengers fare, passengers fare. Let's check count. We check for missing values. We see that age still have a missing values. Passenger fare, no missing value here. Now for X test, again age is missing some values and passenger fare misses one single value. So let's do this. Let's fill all the missing values in train, in test, train, test. Okay, we have some weird warning here, but we could just skip it. It doesn't really matter. We create a new classifier, CLF new, equal to, again, it's equal to decision tree with parameter max depth equals to 5. CLF new dot fit x, again x train, y train, but now it's different x train and y train, right? So they were built from different data. So the target variable is the same, but the data, the axes are actually different. We train our model, and now we could predict on the unseen data. X test, and now we could compute an accuracy score, right? Accuracy score y test compared with y predicted, and the accuracy score is much better. So it's actually like a 10 accuracy points better, about 10, right? So it was 0.67 and it becomes 0.77, right? So it's a 10 accuracy points better, or if we want to compute a percentage, right, it is like 15% better than the original baseline model. And if we compare this number to the random guessing, so basically predicting all the passengers are dead, then it would be even better improvement. It will be like 24% better. And I would say that for the today's purposes, it's pretty good. It's good enough. And this is it for today. This is it for this video, and I hope this video gives you better understanding of what you will do during our class. And see you on Thursday. Goodbye.